All right, so we will go ahead and get started. We are going to finish talking about the main topics from chapter 3 in the text. Remember the quiz, exam, whatever quiz on Thursday is going to cover chapters 1, 2, and 3. And chapter 1 we didn't really talk about. Chapter 1 is kind of the historical aspect, so you want to read that. Definitely want to read that. And we'll keep coming back to some of the historical aspects as we go. So it kind of gives the big picture of what the progression of AI has been and what the focus has been at different times and why, and things that have gone out of fashion and come back into fashion and why they went out and why they came back, and the benefits, at least some benefits, and pros and cons are mentioned there in that chapter. So that one's not like exercises and so on, not algorithms. It's just a historical description mostly of what the field is about. So what we've talked about over the past few, however long it's been now, I've lost track of time. We started with the idea of having an agent or agents. We have agents in an environment. We have some particular goal with a problem formulation. And so all of this, we've looked at the different pieces, right? The things that go into place. Not all the detail that we're going to need for different problems, but those basic ideas. So what does a problem have? A problem has 5 different components that we talked about, right? We have that initial state. The state is the state of the environment at a particular point. We talked about the idea of having this set of actions that are available to us. So what can the agent do at different times? That is more clearly specified in the transition model. So not just what actions are available, but what actions are available from this state. And if you do that action in this state, what state does it put you in? So what state do you transition to? So we then also had the last 2 aspects, which was a goal test function, which means what? As far as automata approach or something, is this an accepting state at that point? Is this a goal that we're trying to reach? And then we also had, that applies in some cases, lots of cases, a path cost function. How much does it cost to transition from this path or from this state to that state? If you use this action and you go from here to here, there's some kind of cost associated with it. What is that cost? All right, and so we had said that the environment then consists of that state space, all the possible states, and we are transitioning from that initial state to a goal state, and any path that gets us from the initial to the goal is a solution to the problem. Right? So whatever path gets us there is a solution. And we talked about optimal solutions, right? If we're using the path cost function, a shortest path is an optimal solution. Sometimes we care about a shortest path, and sometimes we just care about getting a solution. Shortest path, again, can depend on what we're measuring, so there's lots of different aspects of what we're actually measuring. All right, so that's just a rehash of what we've talked about. We spent a couple of days filling in lots of details about the different pieces here. So when we are looking for a path from the initial state to a goal state, We have a couple of approaches. We've drawn some pictures before where you're considering where you go next and what happens. And so we could look at this from the approach of tree searching. Here's where I can possibly go from here. Where can you possibly go from there and there and there? You have everything laid out, everything there available for consideration. And so what happens is, if you're doing a tree search approach, you're going to, or you have the ability, the possibility of considering all possible paths, right? You're considering every possible path that there is from one place to wherever you can get to. If we do a graph search approach, we will then not consider, we'll avoid redundant paths. So we won't consider necessarily the same paths over and over, or duplicate paths. But what happens if you had some kind of rules for creating things? You could just start creating every possible situation. So what we were looking at with the Knuth's 4 problem. We start with 4, and we know what rules are available to us. So in a tree search approach, we could just build everything you can build from 4. What can you build from 4? Remember in that problem, we had 3 things we could do. We could do a square root, we could do a factorial, or we could do a floor. So from 4, what can you create directly? Well, we could do 4 factorial, square root of 4, or the floor of 4. From there, what can you do? 3 things from there, 3 things from there, 3 things from there. And so the tree search approach would just build everything that you can possibly do. I don't know why I just suddenly decided to change the order of things. We would have a consistent order, right, at each level, and say, do this one, then do this one. Okay, so what happens? Looking for a particular number, what could we do? We could just keep building level by level until we got to that number. What if we never got to that number? It might be that we just haven't gone long enough yet, right? Or it might be that it's not possible to get to that number. But if it were possible, we could eventually get there. But what's the idea? There are different ways to choose to search this, right? To search this space. So if we were doing this order, let's say that's the order we're going to apply things in, and we decided to start expanding. If we were doing, say, depth first, what would happen? We're just going to go down one branch, right? It's going to keep going down the factorial branch. Well, are we ever going to get to 5 if we go down the factorial branch every time? No, right? What numbers will we get to? We'll get to 4 factorial, 4 factorial, factorial, 4 factorial, factorial, factorial. We'll get a lot of numbers, but it won't be everything. And if we're searching for a particular number, then what will happen in that method? We will never find the answer, right? If we're looking for 5, can we get to 5? Yeah, we found out that you can get there, but not in that approach. Now, what if we used a different branch? Well, using a different branch, if we change the order of this, then again, depth first isn't going to be able to find there's lots of things that it won't be able to find. All right, so what's the idea? We want to kind of just summarize what the different kinds of searching algorithms are in a different situation, and how to compare and contrast different search methods and so on. All right, so again, nothing new there. So how do we compare search algorithms? Or how do we judge them? Not necessarily compare one to another, but to judge a search algorithm, there are probably four major factors to consider in judging an algorithm. So one of these is the idea of completeness. Completeness is, if there is a solution, will this algorithm find it? Right? So is it guaranteed to find a solution? And again, we're not going to guarantee that it finds a solution if there is no solution, but if a solution does exist, will this method find one of them? All right, so that's the completeness question. If you think back to automata, you had a similar kind of question, a completeness question that was a little different in terms of meaning, but the same kind of idea. All right, so another aspect is optimality. Is the algorithm guaranteed to find an optimal solution? Remember, an optimal solution would be one with shortest path cost. So what could happen? You could have an algorithm that's guaranteed to find a solution, but not guaranteed to find the best solution. Sometimes that's okay, because there are two other considerations in terms of analyzing or comparing or judging an algorithm, and these are time and space complexity. So the time complexity, how long does it take to find a solution? And then space complexity, how much memory is needed? And so sometimes these four things might contradict, or they might work against each other. Right? You want to be able to find a solution if it's there, and it be optimal, guaranteed optimal. That would be the best goal, right? If there is a solution, let's find it. And let's not only find a solution, let's find a best solution. But that might take too much time, or that might take too much space. And so we won't be able to necessarily do that. So we could have completeness without optimality, right? You can find a solution but not guarantee that it's the best solution. Can you have optimality without completeness?
Because optimality would mean you find a solution.
Okay, so what happens in the optimality idea? Maybe it's not worded quite as well as I should have done. The idea of optimality is the solution that the algorithm gives back an optimal solution? So what could happen? An algorithm could say, I can't find a solution. But if it says, here is a solution, then that solution would be optimal.
So like if we have a pathfinding algorithm and there's a wall and the pathfinding algorithm is going a straight line towards the goal, would it be with a high optimality but low completeness?
Okay, so what's the idea? So what's the idea? To have optimality without completeness would be if the algorithm says, here's your solution, then you can trust it that it's good. But the algorithm could say, I don't know. Right? I can't. So the idea is if it gives a solution, then it's correct. But it could say, I don't have an answer for you. Does that make sense?
It's not complete in that it may not find a solution even if it exists, but if it does provide a solution, it's guaranteed to be able to.
Yes. So you can have that optimality idea, right? It might not find a solution. If it's just optimal and not complete, it will not always be able to find a solution, even if one exists. But if it does give you an answer, you know the answer is correct. All right? Whereas completeness, it says, I'll give you an answer. I'll give you an answer every time. And it'll be a solution. It just might not be a best solution. All right? So you think about some algorithms that have to do with, say, Dijkstra's algorithm for finding a shortest path between two nodes. What happens if you have a connected graph and you use Dijkstra's algorithm? You will find an answer, and it will be optimal. What happens if your graph is disconnected? Well, I guess no solution exists, and the algorithm would tell you that. So that wasn't a very good example. Dijkstra's algorithm would tell you there is no solution from this point to that point because you would have an infinity showing up as a label. So not a good example. Switch gears to a different example then. What if you had like an expert system? An expert system is something that you can ask questions and it gives you answers. So if an expert system cannot answer your question, it might tell you, I don't have an answer for you. Or it might just get caught in an infinite loop and just sit there and not give an answer at all, but just keep running. Whereas with an expert system that's actually expert, if it gives you an answer, the idea then is that the answer is a correct answer. Right? So it might not give an answer, but if it does, you can trust it. All right, so what do we have? These four components, and what happens often you already know in a lot of situations where time and space are trade-offs. If you want to save time, you need more space. And if you have less space, it's going to take more time. All right, so when we're comparing or talking about algorithms, this is the kind of questions, these are the kinds of questions we're asking. So what happens in terms of the complexity and all of this? We get ideas of the branching factor, how many things are there to consider, and the depth of a solution. So the depth of a shallowest solution from that tree approach. How far down do you have to go in order to find a solution? Is part of what is tied into determining complexity of a problem. All right. So not of the problem, the complexity in that case of the algorithm, right? It's how much time does that algorithm take, not how much time would any algorithm take, but how much time does that particular algorithm take. All right, so what do we have? Again, questions that we've asked about other things, so it's not really that different than everything that has come before. So we have now mentioned different kinds of search. We have what's called uninformed search. Uninformed search methods are methods that involve not having, you have some information, but not all the kinds of information. And so examples of this we talked about before, breadth first search. Right, so what information do you have? You have some kind of organizational information, but you don't have any heuristics or any extra things, right? You know specific values. And what happens in breadth first, if you're thinking from the tree search approach? You just work your way down level by level in the tree. We have AI folks call it uniform cost search. Uniform cost search is really it's almost Dijkstra's algorithm, which is a couple little tweaks, right? So uniform cost, when you see that in the text, if you look at the algorithm, it's basically doing Dijkstra's algorithm just some very slight modifications about what happens at different points. We have depth first. And what do we know about depth first from our Knuth 4 problem example? Depth first, is it? It doesn't have completeness, right? It's not necessarily complete, depending on how you set things up or depending on what you're looking for. Right? You have branches, and if you get started on the wrong branch, especially with an infinite state system, you can't recover from that. So breadth first, depth first can definitely be problematic in that regard. So there is an approach that modifies that a little bit. There is a depth limited, and all of these are search, right? So a depth limited search. What would depth limited search say? It says that you can only go this many levels deep. And when you get that many levels deep, you just disregard the fact that there are any more descendants at that level. You just cut off the branch and you say, this is as far as I'm allowed to go. Then you go back up and you do whatever's next in the depth first. And you can only go this deep, and then you stop. So what happens? That would keep you from exploring infinitely long branches that are not going to go anywhere. But what happens if your depth that you settle on is one level above where the solution happens to be? Right? The first solution is one level lower than where you've decided to cut things off. So what happens? We still have the incompleteness issue, but maybe not as bad. You would at least know there's no answer within this levels, right? So it kind of ends up having some comparisons to breadth first in that sense, right? Because
more optimal, or not optimal, sorry. Yeah, optimality. Does that give it optimality in the sense that if it doesn't go down a depth path all the way, it will find the optimal solution?
Well, what happens though? You're still going deep here. So you might find a solution deeper here than a more shallow solution over there. So it doesn't give you optimality either. But it can at least prevent that one issue of going too far. So in certain situations, it might give you an optimal answer, and it might give it to you very quickly. But it's not guaranteed to do so. Right? But there are times when you would want to use a method like that. There's another approach that is related to depth first called iterative deepening. What do? You do depth first, but you do with increasing depth lengths. So you start off.
Multiple instances of depth limited going over.
Yeah, it's like multiple instances of depth limited, but then you can increase, if you haven't found a solution yet, you can increase the depth. Keep increasing the depth. And so you're still doing a depth first search, but you can, if you don't find an answer within this level, or within this depth, you can increase the depth. Say, let's look for answers up to 100. Oh, we didn't find any. All right, let's look for answers up to 500 then. Oh, we still didn't find any. Okay, let's look for answers up to 1,000. Oh, we found an answer now. Right? So we don't just search for answers up to 1,000. We search in this iterative kind of process.
So what's the advantage of this over breadth first?
Does that mean you're still limited with the number of iterations you're doing?
Yeah, so you still limit it to the depth. So you have a depth limited approach. But then if you get to that depth and haven't found an answer yet, you can increase the depth.
You can do as many iterations of that.
And keep going. So it's basically iterating the depth limited search, but adding on to it. So what's the advantage? Well, the advantage to this is that it is complete. And as long as we have unit step costs, it is optimal. And It is, at least in time complexity, just comparable to breadth first. You're going back and redoing some things as you increase the depth, and you do a new depth where then you have to redo the things you did up top. But the ones up top aren't where the real issue is, right? The first few nodes aren't the problem. It's the deeper nodes. And so you only redo the deeper nodes so many times. And as far as space complexity, you can do this in linear space. So what happens, this iterative deepening is actually pretty good, right? It wins on lots of, on kind of all four of the characters that we want in a good algorithm.
The thing is, the answer that over back first is that save on space, because back first gives the whole store the whole tree.
Yeah. So what happens in the idea of looking until you find the solution, keeping what do you have to keep from each time, and so on. Yeah. So there are some advantages to modifying in this way. Now, not for every problem though, right? It depends on the problem. That's the idea. That's why there's more than one method, because in some situations one method is going to be better than others. Sometimes some methods will be better in an entire class of problems, and so we want to look at what those might be. There's also a bidirectional. There's some other kinds of things where you kind of look from both ends. If you think about the maze scenario, trying to find a path through a maze, we could look from the start and from the finish. And then what happens? If you ever come together, you can just build the path out of everything. Now, in regular mazes that you got when you were, when you were given when you were a small child, they weren't designed. It would be really easy, just go to the end and work your way backward. But you could have more complicated mazes that are designed with that problem in mind, and says, you are going to try that. And so what could we do? We could build one maze here. You go in there and you come out there. Right? So you go in, you come out. And then build another maze here. But glue them together so that this maze was really supposed to go that way. So that the hard part is that way, and the hard part of this one is going, so this one is difficult in that direction, and this one is difficult in that direction. And you just glue them together, and now trying to go to the end and figure it out doesn't work. If you could find where they're glued together, then you could go one way on one of them and the other way on the other one and get an answer really easily. But you don't know where they're glued together, and you can't figure that out. And so we could do a bidirectional kind of thing that says, okay, start looking on this one, start looking on that one, and then if you come to the middle, yay, we found the solution. All right, so there's other methods, and these are uninformed in the sense that you're just looking at the information about what does it take to get to a next node or to a next state, right? So what is involved in doing that? We also then have, again, all of these are listed in the text and with a lot of detail and algorithms written out and so on. We also have then the informed search methods. And what happens with informed search methods, we have access to a heuristic, something that's going to estimate a solution, the cost of a solution from that point. So we have access. Now, what kind of access is this? It might be something that, it might not be a very good heuristic, but it's a function, something that will estimate the cost to a goal state from state n. All right, so h of n is this function that says, all right, I'm in state n. What's the estimate of the path cost to get to a goal state? And we saw this in with A star and so on. And A star is actually one of these informed search methods. What do we have as far as informed search methods? We could do best first. There's greedy best first. What does greedy best first do? Greedy best first looks at just the heuristic value and expands the node with the smallest h value. All right, so greedy best first is going to expand the nodes with the smallest I'm sorry, those of you who are behind that monitor. We're going to expand the nodes with the smallest heuristic value. What happens in that case is, as is often the case with greedy algorithms, you don't necessarily get optimal solutions, but you get fast solutions. Now, there are some situations where greedy algorithms give you the guaranteed best answer and so on, but in this particular kind of situation, greedy best first is saying, I'm not going to worry about anything but which node do I think is closest to the answer. The node that I think is closest to the answer, that's where I'm going. Then from there, what do I think is closest to the answer? That's where I'm going. Now, what could happen? There could be something that we think is close to the answer, but turns out not to be. Whereas something that we thought was further away let's do it this way. We thought that was close to the answer, so we choose there. But it turns out to be further away than we thought, whereas this other thing that looked maybe that we thought that it was farther away from the answer, it turns out not to be. And so what happens later, this greedy best first doesn't look at, right? It doesn't know what's going to happen. It just thinks it knows what's going to happen. And so you go to the thing that you think is the best answer, which might not turn out to be in the long run. All right, so greedy best first is, again, often very, very, it can be efficient, but it's not necessarily optimal. As far as other algorithms that are informed, then we kind of combine those ideas, and we have A star. And what did we say about A star search? You're taking into consideration not only how far you've come, but also how far you think it is to the solution. And so we minimize that value to consider which nodes to expand. A star then turns out to be complete and optimal, assuming that our heuristic follows the rules, right? We talked about the idea of the heuristic needing to be admissible or consistent. So if you have an admissible an admissible heuristic or a consistent heuristic, admissible in the case of tree search and consistent in the case of graph search, then this algorithm will always find the right answer. So it will find an answer if it exists, and the answer that it finds will be optimal. What's the downside? The downside of A star is that it takes a lot of space. And what can happen in even normal type of problems, A star will run out of space way before it runs out of time. All right?
So A star's example is basically a normal best first algorithm that expands h of n plus our current distance instead of just the smallest h of n.
Yeah. So it's going to minimize. We have how far we've come so far to get to there, plus how far we think it is to the answer. And we minimize that at each step when we're expanding. Which node do we consider next? We'll pick the smallest one of these values. Were there questions?
Does this always get the optimal solution?
Yes. A-star search, again, provided that your heuristic follows the rules that we've talked about before of not being an overestimate and the idea that kind of matches the triangle inequality that going from one place to another is this kind of values. This is always at least as big as that. Right? Which, if you have forgotten those, take a look back at the A-star video that talks about the aspects of the heuristic.
So, are there any other examples that besides distance for heuristic value?
Yeah, so you might not be talking about distance at all. I mean, it might be something that has to do with cost or something to do with time. Whatever kind of thing you're measuring, you can use, back to that idea of the path cost. The path cost might not be distance. We tend to talk about it in terms of distance just because that is easy to think about, especially easy to think about geometrically. But it can be whatever kind of thing you're measuring, as long as it's a numerical measurement that we can describe. Actually, in some cases, when we're implementing these algorithms, especially some of the uninformed, it's not even a numerical calculations that we're doing. It's just like, hey, let's do this alphabetically, or let's do this in some other way. But with a heuristic, it has to be something that we can measure, something we can calculate. So, but it doesn't have to be distance. As a matter of fact, in some cases, focusing on distance might not be what we want to focus on at all. If we care about some kind of financial aspect, focusing on distance or time might cost us more money. And so sometimes, and it depends on the problem. We go back to the original statement of the problem. When you state the problem and you formulate the problem, what do you care about? What is your goal? And that will determine what kind of heuristic that you're looking at. So it doesn't have to be distance. It's just that a lot of what we're dealing with will be measuring distance in some kind of way. You can even measure, you can even create and think about it in terms of, if you were talking about money, we could still create a measurement of how to compare, rather than just actual total dollar amounts. There might be something with, marginal revenue or something that comes into play. So some other aspect of how you're actually measuring, is this better than that? You might not care about the total dollars, you might care about the profit portion. Or you might care about just the revenue generated, which is different than the profit, which is different than total. So there's, depending on what kind of total you're talking about, I guess. Right? So there's a lot of different ways, and we determine that when we set up the problem. And then what kind of heuristic values do we use? Again, that depends on the problem. It depends on how good we are at creating heuristic functions, which again comes back to the idea of sometimes that just requires expert skill set, or just good guessing skills. Of like, here's what I think from here to there. But again, to be admissible, to guarantee that A-star search is going to work correctly, there have to be certain conditions on that heuristic. And you have to be able to satisfy those conditions without knowing what the right answers are. So you have to make sure that your values that you're guessing are not breaking the rules, but without even knowing what the right answers are, to be able to be sure that you're not breaking rules. Sort of make sense? So again, if it comes down to just distance, what do you know? You know that you can never get from here to there in a shorter distance than just a straight line distance. And so you know that straight line distance is never going to be an overguess. Whereas other ways of guessing the distance might be an overguess, and you have to be really, really careful. But you know if you're talking about distance that's never going to be an overguess on that. So what happens with A-star? The issue is not completeness, it's not optimality, it's not time, it's space. So what do? Well, there are a couple of different methods, lots of different methods, but a couple in particular. There's a recursive best first approach, and there's a simplified memory-bounded A star. So there's an algorithm SMA star. Simplified memory-bounded A star. What do you think simplified memory-bounded A star has going for it? All right. Simplified memory-bounded, it uses less memory. It's a robust method. It's optimal. Uses less memory. So what do you think we have to give up? It's time. Right now we have, it's robust. It's optimal. Memory is low, but we have to trade off on time. So time is the problem then. If you have enough time, then you can sometimes solve problems that A star search just ran out of memory on. But the amount of time might be too much. And so certain problems, that just causes a permanent problem, and there's not much we can do about it. That the time and space trade-off, we have to give somewhere, and sometimes, no matter where we give, we can't solve our particular problem. And so what happens, this is kind of just the description of everything that we've been talking about and what the labs have entailed and so on. The uninformed search and informed search. And what are we really doing? We are looking through state spaces and trying to figure out, I started here and I need to get there. How can I get there? But we don't know where there is. Right? All we know is, well, we don't even know that there is a there. But if there is one, we want to be able to find it, and we want to be able to find it as quickly as possible. And so, so all of these different methods exist so that we can, in different situations, be able to apply a method and hopefully be able to find a solution that is guaranteed to be correct. All right. Again, sometimes we don't care about optimality. We talked about the Queen's problem. We don't care about an optimal path to get there. We just care, can you do this? We don't really care the process. The algorithms themselves are helpful in terms of how do you search, how do you get there, but the goal in that case is just to get there, to have 8 queens on the board that behave correctly. So what do we have? Often the hard part is setting up the problem, figuring out how to formulate the problem in a way that we can tackle it. Sometimes the hard part is describing what a potential solution looks like. We will do the Queen's problem in a completely different way soon, and the question will be, how do you even set it up to be able to apply this method? And so being able to recognize what a potential solution looks like is sometimes difficult. Sometimes it's any one of the pieces that we've talked about, any one of them can be the difficult part. Or in real life problems, they all are. Right? It's like, how do you figure out how to set up the problem? Once you figure out how to set it up, what does the environment look like? What's going on? What matters? What doesn't matter? Okay, how do the agents act? What can they do? What are the effects and so on? Sometimes every piece of it can be difficult. But what do we do then? We just take it apart one piece at a time and try to handle that part, try to handle that, try to handle that. But if you focus too much on just one piece, we can often see, like what we saw with this, we focus too much on the memory thing, and we realize that we've given up too much in the time aspect. So all of those kind of trade-offs we have to consider. All right, are there any questions about any of that?